Alright, so today I'm gonna be explaining this important paper with the title Beyond Low Frequency Information in Graph Convolutional Networks. This AAAI paper in 2021. Graph neural networks have been proven to be effective in various network-related tasks. Most existing GNNs usually exploit the low-frequency signals of node features, which gives rise to one fundamental question: is the low-frequency information all we need in real-world applications? So we first present an experimental investigation assessing the roles of low-frequency and high-frequency signals, where the results clearly show that exploring low-frequency signal only is distant from learning an effective node representation in different scenarios. How can we adaptively learn more information beyond low-frequency information in GNNs? A well-informed answer can help GNNs enhance the adaptability. We tackle this challenge and propose a novel frequency adaptation graph convolutional networks with a self-gating mechanism which can adaptively integrate different signals in the process of message passing. We theoretically analyze the roles of low-frequency signals and high-frequency signals on learning node representations. So this is classification accuracy of low-frequency signals, high-frequency signals, and their model is called FAGCN. So the x-axis denotes probability of interconnection. This is interconnection probability, and you see that FAGCN model, this model aggregates low-frequency signals of neighbors, these low-frequency coming from neighbors, within the same class, and high-frequency of signals of neighbors from different classes. So they show the relation between eigenvalues and amplitudes in different filters. So the proposed model is like this. First, a background on this graph Fourier transform. Graph signal processing is a very mature field nowadays, and we can treat the eigenvectors of normalized Laplacian matrix as the basis in the graph Fourier transform. So given a signal, the graph Fourier transform is defined like this. This is the element-wise product of vectors. And this G here is a diagonal matrix and represents the convolutional kernel in the spectral domain. Now we want to separate the low frequency and high frequency. So both of them are helpful for learning node representations, but to make full use of them, we design a low frequency and high frequency filter to separate them. And then here they do aggregation. They first compare aggregation process of existing GNNs and FAGCN. And so the input of our model are node features. These node features, and F here is dimension of the node features. So for the purpose of frequency adaptation, a basic idea is to use the attention mechanism to learn the proportion of low frequency and high frequency signals. So you see the aggregation process of existing GNNs, and this is existing GNNs for existing GNN, but on the right here you see the aggregation process of FAGCN, the proposed model in this paper. And then they have these alpha, as I said, they are proportions of low frequency and high frequency signals. So these alpha are the importance of each node in aggregation here. So in order to learn the coefficients, these alphas, we need to consider the features of both node itself and its neighbors. We propose a shared self-gating mechanism to learn them. After calculating alpha, we can aggregate representations of neighbors. So we first use a multi-layer perceptron to apply non-linear transform to the raw features. Then we propagate representations using this equation. So overall, we can see that here the complexity of single layer GCN is of order of this. And then they talk about the expressive power of that, just like any other method that you introduce. Then they do experiments on these popular benchmarks. As I said, Chameleon and Squirrel are the hardest data sets, and because they have heterophily, very high heterophily, and also they did for node classification. So they compared their model with models like graph isomorphism network, graph convolution networks. And they see the classification accuracy of different methods under different label rates on disassociative network. And their model, they show that it alleviates oversmoothing problem.